Hello, Science Nines. I want to just go over the section 3 and 4 notes, or at least start going over the energy section. I'll make a couple other videos for this one so you can work on it for the next few days. So, as you can see in the notes, energy actually comes from two Greek words, uh, en from within and ergon meaning work. So, as I've defined it, energy is the ability to do work, and it's measured in joules. Joules is actually the last name of James Prescott Joule. He did the science to uh, explain how one form of energy can be converted into another and how it can be measured. The What I want you to be familiar with are the different kinds of energy. So I hope you can see this on the screen well enough. The first type is chemical energy. It's due to the breaking or forming of what are called chemical bonds. So atoms form bonds to other atoms, and if you break those bonds, you release energy. If you form the bonds, that absorbs energy. So that's why I put those two terms in there. And you guys are going to learn about photosynthesis in biology. Uh, what's really clever, it's a great example. The plants take water and carbon dioxide, and they use the energy from sunlight to make sugar, that's C6H12O6, and they also make oxygen, which is awesome. But that requires energy. So that would be absorbing energy from the sun, and then they can take all the hydrogens and carbons and they can arrange them in this big molecule called sugar, that has all these bonds in it. So there's 6 carbons, 12 hydrogens, 6 oxygens. They're all stuck together by bonds. So there's a whole bunch of stored energy in sugar. And of course, we come along and eat that food, or eat the plants, obviously. We break down foods into their simple sugars. And then with oxygen that we inhale, there's reactions that happen where we can break those bonds. So when you break those bonds, we basically break it down and we get carbon dioxide that we exhale and we make some water vapor, but then we release the energy that was tied up in all of those bonds. So in the sugar, there's all those chemical bonds between the carbon, the hydrogen, and the oxygen. Basically cut those and we release energy. So that's called cellular respiration. You guys are going to learn about that in biology. But those are just two quick examples for chemical energy. The next one is electrical energy. And there's a bit of history here just worth mentioning. Alessandro Volta, as you can see, this Italian scientist, he actually he made the first electrochemical cell. He basically took stacks, as you can see here, of moistened paper. I think it was with a type of acid, and he used different metals like copper and zinc and things like that. And he made an electrochemical cell. And yes, of course, one of the units of measuring electricity is named after him. It's the volt, which I'm sure you can see. But he couldn't do too much with an electrochemical cell because no one invented the light bulb or anything like that. But you could run current through a wire. And I know you maybe can't see the bottom picture here. This is Hans Oersted. What he realized is that when you run current through a wire, that wire acts like a magnet. And we call that an electromagnet. That's one of the terms later down in the notes. An electromagnet is basically a coil of wire, or just a wire that when you run current through it, it acts like a magnet. So it'll have a north and a south pole and it will attract and repel things. So, but electrical energy is energy due to moving charges. So if you move electrons through a wire, they can do work. They can do things, right? We can light light bulbs, we can make motors spin, and that is explained. We're going to talk about that a bit later too. Magnetism is basically the attraction and repulsion of metals with north and south poles. There's some energy, or you can witness and experience energy because of the attraction and repulsion. So that combined into actually, it was this man, Michael Faraday. He realized that if you take a magnet and you move it through a coil of wire, so if my hand is a coil of wire and my pen is a magnet, if I take the magnet and I move it through the coil of wire, it actually causes electricity to flow in the loop of wire. It's so simple. It's actually really amazing how easy it is to generate electricity. But Michael Faraday figured this out, and as a result, it quickly led to the electric generator and then also the electric motor, which we're going to talk about in a little bit. So uh, that's a quick overview of electrical and magnetic energy, really. Um, so the next one is thermal. Thermal, you probably recognize as just being heat. And this man, Thomas Seebeck, he realized that he could generate electricity if he heated two different metals at the same time that were touching each other. And this picture shows kind of a candle heating one, like the horizontal metal, and the other metal above it is a different color, so it's a different metal. What I failed to say earlier is that a compass needle will deflect if you place it near a current carrying wire. And the reason for that is, if you've ever played with a compass needle, I should have brought one here, but you can make the needle point in all directions. If you bring a magnet near it, you can force the compass needle to point anywhere that you put the magnet. That's because normally a compass needle will point in terms of magnetic poles. It will point north or south because it lines up with the Earth's magnetic field. The Earth has its own magnetic field. You may have already known that. The Earth generates a huge magnetic field. It's quite weak, but it's very large, and it actually shields the Earth from radiation, does some other cool things. So I'm kind of getting off topic here, but back here, this picture here with Hans Ørsted, it shows a compass needle, and it shows a wire running over it, and that needle actually deflects when you turn the current on, which is evidence that the wire is acting like a magnet. It's making the compass needle do stuff. Okay, so that's exactly what Thomas Seebeck did here when he was heating two different metals, and he basically invented what we call a thermocouple. That's one of the other terms later on, or just down in your notes. And a thermocouple actually converts heat into electrical energy, and this is a picture of it. If you look in your oven at home, you can see up in the top corner there where the light bulb is, kind of the top left-hand corner of your screen. There's a little rod that's sticking out just to the kind of the top and to the left of the light bulb. It's seriously about as long as a pen. Sometimes it can be longer, and it's just sticking out into the oven. That is a thermocouple. You could look at it when next time you put something in the oven. That thermocouple, how it works is, you can see down in this picture, there's a candle here representing heat. But the point of the thermocouple gets heated in the oven, and there are two types of metals. It's called a bimetallic, two metals, like bicycle, bimetallic, basically strips, or bimetallic structure. You have wire A, which is in blue, and wire B, which is in red. They're different metals. One of them is going to heat up faster than the other one because of their properties. And what it does is it actually causes current to flow in the wire. And if there's current flowing, then you can always measure a voltage too. So in my picture here, and I know my face might be blocking it, but there's it shows millivolts. So there's a slight voltage is generated. So the hotter the temperature is, the greater the voltage is, and that can easily be read and analyzed, and then you can know what the temperature is if you calibrate it a little bit. So thermocouples are used in ovens all the time. They're used in your furnace. They're really, really useful because they convert heat into actually electrical current, which can be measured. So the next type of energy is nuclear energy, and it's called nuclear, as it mentions in the notes, because it happens in the nucleus of an atom. This man, Henri Becquerel, if I said his name right in French, he was the first to kind of discover nuclear energy. What you need to know is there's two types of energy. There's energy that comes from fission, which is when you split an atom. So you take a large atom like uranium, and you actually, it will just split on its own over time, but there's ways you can get it to speed up. But when it breaks into smaller atoms, it releases a whole bunch of energy. And most of you are familiar with the atomic bombs that were dropped on Hiroshima and Nagasaki in the Second World War. They used fission. They used the splitting of uranium. One used plutonium. There's other elements that can do it. And they released massive amounts of energy all at once. It was just horrific. We can control that, though, in nuclear reactors, which we'll look at later. So you don't release all the energy at once, but you release it a little bit at a time. And then you can use that to generate electricity. The other type, though, is fusion, and that's combining atoms. So that's when you bring, and usually it's small atoms. So you bring small atoms, like hydrogen is the smallest atom out there. And that's actually what stars do, is they take hydrogen, and gravity helps in the process, but it fuses hydrogen atoms together, and then they make helium. And when you do that process, you release energy again. So that's actually where all the energy, the bulk of the energy from our sun is coming from. Our sun and our solar system is fusing hydrogen to make helium, and it's releasing light and heat. And that's from fusion. So that's another form of energy. Sorry, actually, I guess here's the picture of it. Solar energy really is coming from fusion. And originally, scientists thought that the sun was burning, actually, like it was a big bonfire of something that was just burning. And that didn't add up, though, because the sun should have burned out a long time ago if it was actually doing combustion. It's not doing combustion. Scientists figured out eventually that it's fusion. And that explains where we get all the energy from our sun. So this is a little bit out of order, but mechanical energy is the energy due to position and motion. And Isaac Newton, in his laws of physics, explained that. And you guys won't do a lot with the energy of position and motion until you get to Science 10, but those combined are mechanical energy. And I think I listed that down there again a little bit towards the end of that first part. So that covers the first part on energy. So I'll make another video shortly on the remaining notes.